Hello everyone. In this video, I'll be discussing about frequency divider circuits. A frequency divider circuit is a digital circuit that takes an input clock signal of a certain frequency and produces an output signal with a lower frequency, typically an integer fraction of the original. Frequency division is an essential feature in digital designs. In modern systems, a chip may have multiple sub-blocks, and some of these blocks require lower clock frequencies to operate correctly. Instead of using multiple oscillators to generate different clock signals, a frequency divider allows us to derive all the required slower clocks from a single high frequency source. In this discussion, we'll focus on the circuits that generate clock signals with frequencies equal to 1 over 2 to the power n of the input clock frequency. Depending on the implementation, it can be an asynchronous or a synchronous frequency divider circuit. First, let's look at the basic concept used to design an asynchronous frequency divider. To design this, we use a D flip-flop. In this D flip-flop, apply a clock signal CLK of frequency F at the clock pin. Further, connect the Qn, that is Q bar or inverted Q, back to the input D of the flip-flop. In this circuit, output Q toggles on every active edge of the clock, producing a signal of frequency f over 2. Equivalently, if the period of the signal CLK is t, the period of the signal generated at Q is 2t. Applying this basic concept just with one D flip-flop, we can design a divide by 2 frequency circuit. To generate a signal of frequency f over 4, we extend the divide by 2 circuit. First, we construct a divide by 2 circuit using a D flip-flop FF0 as described earlier. Then we used a second flip-flop and then connect the FF1QN back to FF1D. Also, drive the clock input of FF1 by FF0QN. When this circuit operates, FF0 divides the input clock signal of frequency f by 2, and a signal of frequency f over 2 is available at FF0Q. FF1 receives a signal from FF0QN of frequency f over 2 at its clock input. Due to the feedback, FF1Q toggles on every active edge of its clock input, that is FF0QN, and thus FF1Q produces a signal that has a frequency of f over 4. In terms of time period, if the input clock CLK has time period t, the time period of signal at FF1Q is 4t. A divide by 8 circuit is further extension of divide by 4 circuit. To design it, start with a divide by 4 circuit using FF0 and FF1 and then add a third flip-flop FF2. In this circuit, drive FF2 clock from FF1QN and connect FF2QN back to FF2D input. During the operation, FF0 generates a signal at Q that is of frequency f over 2. FF1 further divides the output FF0Q and generates output FF1Q that is of frequency f over 4. FF2 receives the signal FF1QN of frequency f over 4 at its clock input and toggles output Q on every active edge of the clock input, producing a signal of f over 8 at FF2Q. In terms of time period, we can see that if the input clock signal CLK has time period of t, the time period for FF2Q is 8t. We can observe that by cascading n such D flip-flop or stages of D flip-flop, where each stage clock is driven by previous state's Qn signal, we obtain a ripple divider that divides the input frequency by 2 to the power n. Here we have 3 stages, so the output frequency at FF2Q is f over 8. This asynchronous frequency divider is essentially an asynchronous ripple counter, capable of counting from 0 to 2 to the power n minus 1, where n is the number of flip-flops. Now let's look at synchronous frequency dividers. In synchronous frequency dividers, all flip-flops are clocked by the same clock signal, so they operate in parallel unlike the ripple approach in asynchronous dividers, where the stages are triggered sequentially. This eliminates the cumulative delay present in ripple dividers, making synchronous designs faster and more reliable at higher frequencies. To design a divide by 2 synchronous circuit, use a single D flip-flop with feedback Q and fed back to D input and drive the clock signal at frequency F at the clock input. On every active edge of the clock, the output Q toggles. Therefore, the signal generated at output Q has a frequency of F over 2. Now let's discuss how to design a synchronous divide by 4 circuit using two D flip-flops, both clocked by the same clock signal CLK. Earlier, we designed a circuit with a single D flip-flop that generates an output signal of frequency F over 2. Now, starting from the signal with frequency f over 2, we want to derive a signal of frequency f over 4 at the output of ff1 as shown over here. This is our expected divide by 4 output. A key step is to determine the correct input for ff1d. If we examine the signal ff1q, which is toggling at the frequency of f over 4, we notice that the updated value at the next rising edge of the clock is given by ff0q XORed with ff1q. For example, when ff0q is 1 and ff1q is 0, then the XOR of these two values are 1 and hence ff1q will be updated to 1 at the next rising edge. Now let's look at this clock cycle. If ff0q is 1 and ff1q is 1, the XOR of these two signal is 0 and hence ff1q is updated to 0 at the next rising edge. This pattern continues to generate the expected output. Thus, by connecting ff0q XORed with ff1q to the D input of ff1 flop, we obtain the synchronous divide by 4 circuit. To design a divide by 8 synchronous circuit, we extend the idea using 3D flip-flops. ff0q has a frequency of f over 2, ff1q has a frequency of f over 4, and ff2, that is the third flip-flop output, must have a frequency of f over 8, which is also the expected output. Now let's determine the correct input for ff2d. If we examine signal ff2q, which is toggling at the frequency of f over 8, we observe that the updated value at the next rising edge is given by ff0q and ff1q ANDed together and then XORed with ff2q. For example, in this clock cycle, ff0q is 0 and ff1q is 0. AND of these two is 0, XORed with ff2q gives a 0, so ff2q stays at 0. In the second clock cycle, AND of these two signal is 0. A 0 XORed with 0 gives a 0, so the value of ff2q stays at 0. Over here, in this particular clock cycle, ff0q is 1 and ff1q is also 1. The AND of these two is 1. This one XORed with ff2q gives a 1, and this is why ff2q toggles to 1 at the next rising edge. Thus, by connecting ff0q ANDed with ff1q and XORed with ff2q to the D input of ff2 flop, we obtain synchronous divide by 8 circuit. A synchronous frequency divider circuit can use n flip-flops, all clocked by the same input clock signal, where each flip-flop's next state is determined by the combinational logic, often using XOR and AND network, so that the counter progresses at active edge of the clock. The outputs of the flop correspond progressively to the divided frequencies. We can observe that both synchronous and asynchronous frequency dividers can be used as binary counters, counting from 0 up to 2 to the power n minus 1, while simultaneously producing divided clock signals of frequency f over 2 to the power n. This is all for this video. Hope this is helpful.